Okay, I think today we should start on the next unit topic, which is space and time. Yeah. I hope you've all had a chance to look over the reading. There's, I guess, a number of readings. Hi. The two main ones, though, were the Van Cleve article on space and time in the Companion to Metaphysics, and then the entry in the Historical Dictionary on space and time, and then there were some other additional ones, the entry on McTaggart in the Historical Dictionary, and a bunch of other entries as well. So that I'd start off with some stage setting, sort of big picture overview of all the different issues, and then we'll look at a selected number of them in more depth, or if you have specific questions about any of these, have a special interest in one of them, we could delve into it at that point. So there are a number of different ways of approaching it. One aspect of the problem is sort of mathematical in nature. I mean, if you think of geometry, say, as a mathematical science, an a priori mathematical science, and you ask what its subject matter is. In some sense, the subject matter of geometry concerns space, or at least basic spatial properties and the relations among things in space, in some sense. So one could view geometry as a kind of science of space in some very general sense. It's also true at the same time that physicists study space and time as well. Thought that arithmetic was sort of the study of things in time. You can put things in time into a numerical sequence, right? Like the hands of a clock, right? Unnumbered. But leaving that aside for the moment, it seems clearer that geometry has something to do with space, even if arithmetic doesn't concern time. But arguably, at least one important philosopher thought that it did. But as I was saying, physicists study space and time as well, so it seems problematic that space and time are the sole objects of a priori sciences. There seems to be an empirical study of space and time as well in physics. So we're faced with the problem of reconciling these two different approaches. That's one of the important themes. Clearly there's an interplay between what geometry studies and what physicists study. Both are concerned with how objects are related to one another in space, but the question is, are they studying the very same relations and properties? Looking at it first from a geometrical point of view, it appears that, theoretically speaking, there are an infinite number of possible spaces which have different characteristics. Some of these fundamental some of the fundamental characteristics are understood in terms of mathematical concepts like the degree of curvature that a given space has, or the number of dimensions that a given space has. So a given space will have both the curvature and a certain number of dimensions. So in elementary Euclidean geometry, we study the geometry or space of a perfectly flat surface. So it has zero curvature, right? It's not curved. It's a flat surface. And how many dimensions would it have? Flat. Say the surface of the tabletop, and if you imagine it extended out in all four directions infinitely, you have what's called the Euclidean plane, named after Euclid, the great Greek geometer. So how many dimensions does a plane have? It has two. It has width and breadth. So what we call three-dimensional space has a third dimension to it as well, depth. Right, so you can have three lines all perpendicular to a given point in a three-dimensional space. A line has only one dimension, which is length, and a single point has zero dimensions. Not much room in there for anything to go on. So going beyond three dimensions is more difficult to conceive or imagine. But mathematically, there are four-dimensional spaces and five-dimensional spaces, and there's no end adding more and more dimensions. There are also non-flat spaces. So, for example, there's a space which is the congruent to the, say, surface of a sphere. A spherical surface constitutes a different kind of space than a geometry of a flat plane. So it has a degree of curvature, positive degree of curvature to it. And you can imagine other kinds of spaces, right? Ones that undulate, curve in all kinds of different ways. And you could have four-dimensional spaces, which are Euclidean or non-Euclidean, and so on. So there's all kinds of combinations of dimensionality and curvature that lead to infinitely many different possible spaces. So one might think of geometry or topology in principle as the science of all the possible spaces and properties and relations among the objects in them. I should also mention that there are spaces that have negative curvature as well as positive curvature. So the simplest example is the surface of a saddle, which is also referred to as a hyperbolic space. A saddle surface is at one end, and then you have the spherical surface at the other, and sort of the Euclidean flat plane in the middle. And then there are analogs of these in 3 dimensions, and 4 dimensions, and 5 dimensions, and so on and so forth. So all of that's in the realm of possible spaces. So you might then view the tension between what physicists do and mathematicians who study geometry do in the following way, that the mathematical principles of geometry, which apply to different respective possible spaces, like Euclidean and spherical and hyperbolic and different dimensions and so on and so forth. These principles, mathematical principles, geometrical principles, can be, at least some of them, well, no, I should say all of them, can be known a priori and are necessarily true. So it's necessarily true in a Euclidean space that, say, for any given straight line, there is one and only one line parallel to that given line. So if you have a given line here in a flat plane and a point out here, P, there'll be just one straight line through P that will not intersect the original line, which is the parallel, which is equidistant at all points from the given line. So that's what's true in a Euclidean two-dimensional space. It's different, though, in a spherical space. On the surface of a sphere, you don't have any straight lines, right? Not in the sense in which you have them in the Euclidean space. There, instead, you have what are called great circles. They're the shortest distance between 2 points on the surface of a sphere. So, in a Euclidean space, the shortest distance between 2 points is a straight line, but on a sphere, the shortest distance is a curve, which if you extend it all the way around forms what's called a great circle. So in aviation, pilots try to fly on a great circle around the globe to get the shortest point between their departure city and the destination. It'll be like an arc, right? Connecting one to the other. So these principles are each necessarily true in relation to the space that they're in, at least. So in a Euclidean space, right, there'll be one and only one parallel. But in a spherical space, actually, there are no parallels to a given great circle, because all the great circles intersect, like at the poles. They'll all intersect each other. And there are many that intersect. So you don't have any parallels at all. There are no non-intersecting great circles passing through a point outside a given great circle. All great circles intersect at some point. So you have no parallel lines. But there aren't any straight lines either. They're called geodesics. Geodesic is the shortest distance between 2 points in a given space. So straight lines are the geodesics in the Euclidean plane, and great circles are the geodesics on a spherical surface. And what about on the saddle? On the saddle, they're kind of arcs that, well, they're reverse arcs, or other sort of things like that, right? That are the geodesics. And there you can have many parallels to a given geodesic. Because they'll sort of, they'll approach the given line without ever touching it. And they'll never meet the given line, though they're always getting closer to it. And there'll be many such geodesics with respect to a given line. And that's a necessarily true principle. So it seems that we could understand geometry as a necessarily true science studying the intrinsic properties and relations holding with respect to a possible space of a given sort. And we can know, the important thing here is that we can know these, the basic axioms of these systems just by reflecting on them. We can see that all great circles will intersect on a sphere, but that there'll be one parallel that doesn't intersect, given geodesic or straight line in the Euclidean plane. We can know these to be these axioms or what follows from them, which are known as theorems. We can know these axioms and theorems through a priori insight or deductive inference from the axioms. We can know this without having any empirical evidence, because we're talking about possible spaces here. And the question of what geometry actual space has can't be known a priori. At least that's a consensus among contemporary philosophers, and I certainly have no reason to doubt that that's true. It's an empirical question what geometry actual space has, because you have all these different possible geometries to choose from. For thousands of years, people thought that space had to be Euclidean. Well, first of all, it appears to be Euclidean, but so does the surface of the Earth, too. Right? Close up, any very large space will appear to be Euclidean to creatures that are relatively small in relation to that space. That doesn't prove that it actually is Euclidean in the large, as we see with the Earth. Right? I mean, the Earth seems flat to us. If we draw a triangle on the beach and measure it, they'll fall within the constraints of the axioms of Euclidean geometry within experimental error. Since our rulers and measuring devices are not exact either, we don't have any reason to believe that the Earth isn't flat until we go on a bigger scale and find out that if we go on a long enough journey, we're going to come back to where we started. Then we know for sure that it must have been round or spherical. So for many thousands of years, when you take that fact, the fact that in the small, most spaces will appear to be Euclidean if they're sufficiently large and the observers are sufficiently small. Together with the fact that we find it very, very difficult or impossible to conceive of a three-dimensional space that's not Euclidean, we can't actually picture it very easily. We can't imagine, say, what it would be like to be in this curved space. I'm not sure that that's actually true. That's often claimed that we can't imagine it, but I'm not sure actually that we've tried hard enough to imagine it. One might actually be able to sort of have a sense of what it's like. I mean, have you ever looked through, imagine one of those little things they have in hotel rooms, where you look out the peephole, and it's got like a lens in it, and you look out into the corridor. And it's curved, so it gives you like a fisheye perception of the hallway that seems sort of, right, curved around. It's not clear to me why that isn't an experience of what, there you're seeing in three dimensions, right? It's not just a curved surface you're seeing a whole hallway and all the doors sort of curved around. It seems like if one had experiences like that and reflected on them, one would get the sense of the curved three-dimensional space. It's a quite small one, where you can actually see the curvature. In a really big one, it's not going to look any different than our ordinary space does, just like the Earth seems flat in two dimensions. The surface of the Earth, a two-dimensional thing, seems flat to us, even though we know it's round. So maybe one can conceive of these curved spaces. Conceiving of higher dimensions is more difficult. Like a fourth or fifth spatial dimension. There it seems like we have to go with analogs. So, I mean, the process of analogy is something like this. To get to a three-dimensional cube from a square, you have two squares, right? And then you connect the edges of the two squares, and you get a cube, right? A two-dimensional representation of a three-dimensional object. So we need a three-dimensional representation, since we can only perceive three dimensions. We need a three-dimensional representation of a four-dimensional object, but it seems like you could do that, right? You could make one of those. So if you take two cubes and then connect all their edges together, that would give you, say, a three-dimensional representation of a four-dimensional cube, which is called a tesseract. It would just be a representation, though. We seem to not have the ability, most of us, and I don't, to imagine a fourth spatial dimension that's at right angles to the three that we have. I mean, if you could do that, and imagine a sphere that's hollowed out, and you were inside that sphere, right? If there was a fourth dimension, or if you could imagine one, you could imagine a way of getting out of the sphere without actually going through the wall, without perforating the surface, say, that encloses you, by just going into that, right, fourth dimension and stepping over the. I mean, just like if you're inside a two-dimensional square, right? You could just get out of it without going through the sides, right? How would you do? You would just walk over right? You would just stand up and walk over the side, right? And you'd be out of it without perforating the side of the square. So if there was a fourth dimension of space that we had access to, or someone had access to, you just step out of the cube or the sphere or whatever by going into the fourth dimension and walking out. Right? And that's what it would be like. But we can't visualize that, having grown up in a three-dimensional world. Now, some physicists have postulated in string theory that there are actually 11 dimensions, just a theory, in our actual world, 11 spatial dimensions. But apparently they only exist at super microscopic levels in the micro world. So there are these other degrees of freedom or dimensions you can go into spatial, but we have no experience of them. So I guess like blind people who can't see certain colors, we have no idea what these dimensions are actually like. They're so tiny. We can't perceive anything on that scale, on the scale of electrons. It's totally beyond us. So even if string theory is true, there's not a great deal of evidence supporting string theory this time. But if it turns out to be right, then there would actually turn out to be 11 dimensions. So there'd be, I guess, eight more spatial dimensions in addition to the 3 that we know about. One point that should be clarified here is talk about time as the 4th dimension. Sometimes it's said that Einstein showed that we live in a 4-dimensional world, and time is the 4th dimension, together with 3 spatial dimensions. That's different than saying there are 4 spatial dimensions. So if you view time as a 4th dimension, as relativity theory does, then what you're saying is that space and time together form a single unit called a space-time continuum. This space-time continuum concept implies that there's a single entity called space-time. In this single entity, space-time, has 4 dimensions to it, 3 spatial dimensions and 1 temporal dimension. The previous view held before pre-Einstein was that there were 2 separate things, space and time, that were separate from one another rather than one continuum of the 2 melded together. There was space, which had 3 dimensions, or which was believed to have 3 dimensions, and time, which had 1 dimension, sort of a linear thing, right? It has, it goes from the past, say, into the present, and then on to the future. So it's just sort of a number line that goes in one direction from past to future. So that would have 1 dimension. But if you put the 2 together, you get this 4-dimensional thing. 3 spatial dimensions and 1 temporal dimension. The 4-dimensional space-time continuum. Something out of like Star Trek. Okay, so at any rate, it looks like a plausible thesis in light of current views about the nature of mathematics and geometry, including geometry, and also physics, which studies the nature of actual space, as opposed to geometry, which studies the logical structure of all possible, logical or mathematical structure of all possible spaces, is that geometry and topology are a priori explorations into the necessary properties and relations of each kind of possible space, whereas physics uncovers empirical evidence for the hypothesis that our actual space has a particular geometry, which is a contingent matter. So our actual space might have been Euclidean or spherical or this or that or the other. It might have had 3 dimensions or 7 dimensions or 11 dimensions. It might be curved or flat or whatever. It's up to physics to investigate this through empirical experimentation. So that might be called applied geometry. And then you have pure geometry, which is what mathematics pursues. Pure geometry uncovers necessary truths knowable a priori, either through direct intuition or through logical deduction from axioms which are directly intuitive. Physics involves an inquiry into which of the possible spaces is exemplified by actual space, and it introduces empirical evidence in support of one of those. The hypothesis that our actual space has a particular given geometry. Einstein at one point hypothesized that actual space is curved. So if you go on a big enough scale, say it's some kind of gigantic sphere, 4-dimensional spherical system. Scientists are still debating what geometrical structure actual space has. According to Einstein's theories, it's known or believed to be known, it's hypothesized that a very strong gravitational field will cause space to bend. So space, I guess, would have a kind of irregular, it might be, say, Euclidean in some parts and then, say, curved in some way in a different part and so on. there's no particular evidence supporting the idea that it's a giant sphere or anything like that, that you would come back to your starting point. Rather, the theory seems to be that it's expanding all the time, so it looks like it's sort of open-ended and just sort of rushing out. It doesn't have any particular, doesn't seem to be limited or finite. Given the notion of a four-dimensional space-time, which is also involved in contemporary physics, originally posited by a gentleman named Minkowski, so it's also known as Minkowski space-time. Was used by Einstein in his theories. If the universe is expanding, as all the astrophysicists tell us, and will keep expanding, which seems to be what they're telling us from their observations and theories. If we adopt the space-time view, that the universe is a four-dimensional space-time manifold, given the assumption that the universe will keep expanding, say, indefinitely, or that time is infinite, at least in the forward direction, that's not going to come to an end at any point. If we can make those assumptions, it's hard to see how it would stop at some point. Physical laws seem to say that so long as anything exists, it'll keep on moving. So if time goes forever, I mean, it might be that things would just totally vanish at some point or something. Universe would just blip out of existence, say. I mean, you could imagine that occurring as well, but it seems sort of strange to suppose that everything would just disappear. And if we assume that things continue in some form or other, time would be infinite, and the universe keeps expanding. It would seem that the space-time continuum would be infinite then, both in space and time. And as a four-dimensional space-time continuum would certainly be infinite, unless somehow everything vanished. So that would be my argument for the infinity of space-time. But of course, it's based on empirical assumptions. It's applied, it's a scientific theory. So we don't really know, right, what would happen, say, a Googleplex years out, whether everything could vanish at some point for some reason, whether it would endure. So we'll never really be able to, with any degree of certainty, without making just certain plausibility assumptions. We don't have any way of defending. This is kind of Hume's position. Ultimate questions of the universe, one of skepticism, at least when it comes to the actual universe. That's the nice thing about pure geometry. There, you can know a priori what the properties of a spherical, nine-dimensional space are. It's all necessarily true and a priori. There's a third, there's another view, or a third position one could have with respect to the geometry of the actual universe, questions about the geometry of the actual universe. Van Cleve talks about a view that he calls conventionalism. According to conventionalism, sort of a skeptical view. It says we really can't conclusively determine the geometry of actual space. Like we make certain assumptions, and based on those assumptions, we can conclude, say, that it's simplest for us to suppose that space has this geometry or that geometry or whatever. But it's just based on making an assumption that can't be verified about whether objects retain the same geometrical properties, say of congruence, when they're moved. So two objects are congruent, say when you can superimpose them on each other and they line up perfectly, right? Like two right-hand gloves at exactly the same size are congruent, right? Superimpose one on the other, right? But what would happen when you move the gloves apart? Did they remain congruent? Suppose you have one glove on the North Pole and one glove on the South Pole. We assume that they are still congruent, but we can't verify that conclusively because we can't superimpose them when one's at one pole and the other pole. Right? So we make an assumption that things that are moved remain congruent. But the conventionalist says that's just an assumption. So these conventionalists kind of are logical positive, are influenced by logical positivism, and they say if you can't verify it, you can't really accept it. So they say we just assume it is by convention. And given that assumption, we can reach all kinds of views about what the geometry of space, or actual space is. But you could make a different assumption, they say, and get a different result than about the geometry of space. So they kind of hold a view that you make certain assumptions about the sizes, say, of things, or whether they're congruent or not, based on practicality. They're not really verifiable. So there's no way of really knowing what geometry space has. Relative to certain assumptions we make, we can say that it has this geometry or that. But those assumptions themselves are just assumptions that we adopt by deciding to agree on them. But we can't establish. So that's the conventionalist view. So they would say that space is kind of this kind of like amorphous thing. It doesn't really have any definite geometry. We decide to use a certain geometry because it's practical for us to do it that way. So they're sort of skeptics about a knowledge of the geometry of actual space. This skepticism doesn't affect pure geometry at all. Pure geometry studies the necessary nature of a given space, knowable a priori. It's only applied geometry trying to figure out the shape of our actual space. And if you go to the geometry of our actual space, that's much more uncertain. So here, you can have this conventionalist view. Scientific realists want to oppose this kind of conventionalist view. They want to say we can actually have strong scientific reason to attribute a particular geometry to space. Because I guess on the grounds that a particular theory is the best explanation of the phenomenon, they're not skeptics about this. They would say that simplicity has epistemic validity to it. That a theory is simple and provides the best explanation of the data and so forth actually gives us strong reason to believe, adequate reason to believe that the theory is true. It's not just a matter of accepting something because it's simpler or easier for us to make that assumption. They don't believe the assumptions are just arbitrary. The conventions that we adopt about objects and their congruence when moved are just arbitrary and relative to your preference for whatever purposes you have. They reject that. Now, some philosophers influenced by Plato have held that these geometric necessities that pure geometry studies, like the Pythagorean theorem, say in the Euclidean space, that these necessities hold in virtue of necessary relationships among properties. say among Platonic necessarily existing properties. So that, remember one of our truths about properties was there are shapes that are unexemplified, right? And it was difficult for the nominalists to translate that into a statement about concrete things only. So that, say, being a 114-dimensional triangle or cube or something like that would be one of these unexemplified properties. So just to connect this to what we did earlier. So one might think then that geometry is ultimately grounded in necessary truths about abstract universals of shape. Another view, which is more nominalistic, but still says that geometry is true in virtue of relations among abstract entities, is the idea that geometry can be reduced to set theory. The idea is that we can represent all the points of space in terms of sets of numbers. So for every point, there's a real number, right? Consisting, say, of 3 indices, right? In terms of the 3 dimensions of space. Right? So this point here, right, represented by a ordered triple of 3 numbers, which are, say, its relation to some point of origin in terms of the map of space that we have. So the idea is then we have sets of these points, so we can understand all of the truths of geometry in terms of set theory. So then you wouldn't need these abstract universals to do geometry if that's true. Then space would sort of vanish, right, as an entity, so to speak. Why would we need space anymore? Right? We could represent it, reduce it to sets of points, and the points would become sets of numbers. So we'd have sets of numbers, and numbers would be sets of sets, and so we'd have sets of sets. It would all be understandable in terms of sets. It's just a theory, metaphysical theory. Another view that David Hume held was that necessary truths of geometry are relations of ideas, where ideas are kind of mental entities of some sort. At least that's how we would think of them nowadays. Hume actually had a kind of neutral view. He thought that both the concept of a mind and the concept of a material thing were like equally vacuous, and that the basic particulars of the world, the basic concrete particulars, were what he called impressions. So impressions were a little direct experiences of color and shape, right? Odor, taste, and pain and pleasure and so forth. So there were these basic concrete particulars, impressions, and ideas were copies, mental copies of the ideas, of the impressions. So an idea of, say, a square would be a faint copy. So it's a copy of an impression. So you actually see a square, that would be the impression of squareness. And then there would be this copy that we make of it. When we think about it, then we retain. And it has less force and liveliness to it than the impression does. So the idea is kind of So if you think of a square when you're not looking at one, then you have the idea of squareness before you, or your idea of squareness. So the claim is that both impressions and ideas are concrete particulars. And then the further claim is that geometry is the geometrical necessities are knowable a priori and are merely relations, are true in virtue of relations among these ideas. So the ideas are copied from the impressions, and then geometry is necessarily true in virtue of relations that hold among, say, my idea of a square and my idea of a triangle and my idea of a circle and so on, which are copied from concrete experiences of these things. So that's Hume's view. Okay, now I'm going to go on here to say a little bit about Zeno, the ancient Greek philosopher. He was very skeptical. He was a member of the Eleatic school. The Eleatics distrusted their senses. They were very rationalistic. They thought that we could know the ultimate nature of the universe only through reason. The founder of the Eleatic school, and they were called the Eleatics because they lived in a place in Italy called Elea, E-L-E-A. So they lived in Elea, and they were known as the Eleatics. The first of them was Parmenides. And then there was Melissus, who was a student of Parmenides, and Zeno, who defended the Parmenidean view. Parmenides believed that through reason we could come to know that only one thing existed in the universe. That the universe just consisted of one thing, which he thought to be, Parmenides thought to be seems to have thought to be, because it's hard to interpret these philosophers when we just have, 3 pages of their writings, which is all we have of these very ancient philosophers. We have fragments and little stories about them that other people wrote them. Anyway, Parmenides thought there was this one thing which he seemed to believe was a very large spherical object, because the Greeks were into spheres, and stuff, because they had the most symmetry and were the most divine, right? Because of their symmetry, and spheres and circles are more symmetrical than circles and squares. So, at any rate, later Eleatics like Melissus didn't necessarily agree with Parmenides about that, about the geometry of the one thing. Melissus seemed to think that the one thing was infinite, whereas Parmenides seemed to think it was finite. But if it was finite, it had to be round. But it could also, Melissus reasoned that it had to be infinite. So they didn't necessarily agree about that. Zeno, though, was very skeptical, so skeptical of the senses, and defended the Parmenidean view, which said that there was just one necessarily existing thing and that it never changed. So Parmenides' big argument for all this, by the way, was that you can't have change or multiplicity. So multiplicity is having many things, and change is when a thing obviously goes from being in one state to being in a different state, right? Like an object could be brown and then become white. Change its state of being brown, brown was altered and it became white, right? Like if your hair turns from being brown to white as you age. So according to Parmenides, if a thing for a thing to, for there to be many things, or for a thing to change in any way, there would have to be negativity. So if a thing changed from being brown to white, then the thing would have changed from being brown to not brown, right? And not brown would be negativity, right? And negative. According to Parmenides, though, there can't be any negativity. Parmenides says all that can exist is existence. There can't exist non-existence. He takes this as this kind of obvious axiom that there can't exist anything that doesn't exist. So Parmenides rejects negativity altogether, negative anythings. So according to him, the universe must be completely full, because if there was a lack of anything, that would be non-existence having existence. Being, non-being would have being, which is impossible, he says. He also argues that we can't think of non-being, that we can only think of being, of things that exist. We can't think of non-existence. Because if we did, we'd be related to something that doesn't exist, and that's impossible. How can there be a relation between what exists and what doesn't exist? Like tapping a non-existent person on their shoulder. Really hard to do, right? So there can't be a relation of tapping between my hand on a non-existent thing. So for him, there can only be being, can only exist existing things. So negativity or non-existence or non-being is always ruled out. So therefore, there can't be, first of all, any change, because change would be going from something's existing to its nothing, from brown existing here to non-brown existing here. So there's no change. There's no coming into being or passing away. There's only, and there can't be more than one thing, because there have to be then gaps between things. But that would be non-being. So for there to be two things, there'd have to be this thing and this thing with something separating them. But that would be negativity. There'd be a vacuum between the two things. So ultimately we get to that there's just one big thing. And right, so we're all in this together. We're just all one. There's just this one big thing. All diversity and multiplicity is an illusion of the senses. All change is an illusion of the senses. So Zeno took this up and defended skepticism of the senses with respect to change and motion and so forth, and plurality. He said all of these are delusions of the senses. Our belief that there are many chairs in the room, our belief that a chair can move from one place to another. So these are all delusions of our senses. And he claimed through his paradox, he had a number of paradoxes. There were four main paradoxes of motion in particular that he had. He had other paradoxes attacking other sensory perceptions. With respect to skepticism about motion, he attempted to prove the impossibility of motion altogether, saying that whenever you see anything move, like this blackboard eraser, it's an illusion, an delusion caused by our senses, but we can know through reason that nothing could ever move. So if you, in your reader dictionary here, if you go to Zeno, you'll see a sketch of some of these paradoxes of motion. Actually, he's said to have composed some 40 arguments in support of Parmenides, but a lot of them were lost. Yeah, it's very sad that so many great things get lost. Right? I was watching a movie last night. There's this famous artist in Holland, one of the Dutch masters, Vermeer, and tons of his things have been lost. So many, in fact, that forgers started like creating copies of these lost things and passing them off as the original. So no one's really sure about any of his paintings anymore. They're actually done by him, forgeries. It's very sad. they have pretty good evidence that some of them are originals. But whenever a new one is found, they're not really sure like what it is. So there's a whole vast study that has to be undertaken to calculate the probability that it's actually painted by the artist as opposed to being an ingenious forgery. At any rate, most of Zeno's arguments against motion involve the idea of infinity. So this would be an important result if we found out that there's no motion in the world at all. I'll sketch two of the arguments. One of the arguments is a famous argument about the race between Achilles and the tortoise. And so, who was Achilles? He was that guy.
Greek hero in Odyssey. Or the Iliad.
Iliad.
Yeah.
Odysseus was in Genesis. Right. So, remember there was that movie about Troy? What was it, like Brad Pitt or something?
Yeah.
Yeah, so,
Brad Pitt.
yeah, Brad Pitt was he jumped a lot, right?
Yeah.
You remember that one. So the big thing with him was he had a weak heel, otherwise he was invulnerable, because his mother dipped him in the mystical river Styx as an infant, but had to hold him by the heel. If you're dipped in that river, you're invulnerable to harm. But he was held by the heel here, so his hand covered that part, so it didn't get dipped. So that's how they finally got him, right? They shot him like 100 times in the heel with an arrow. Otherwise, he was impervious. Anyway, so Zeno did a thought experiment where he said, let's have Achilles in a race with a tortoise. So Achilles was reputed to be the fastest, fleetest runner, right? In Greece as well. So he could do the 100-yard dash in 8.6 seconds. He was really fast. And the tortoise is very slow, right? So creeping along. Yeah. So Zeno argues that if Achilles gave the tortoise a head start in a race, that Achilles would never catch up to the tortoise, which conflicts with what we think we know based on our sensory perceptions of motion. We think we know that if Achilles gave the tortoise a head start, that Achilles would win the race, right? I mean, suppose it's a mile race and he gives the tortoise, say, a 50-yard head start. So here's your tortoise. Say your starting point is back here, and then the finish line is way down here. So Achilles gives him a head start, so the tortoise gets to start over here, say, and Achilles is starting here. So we know the tortoise is going to be creeping along, right? Achilles going like really fast. He's going to pass that tortoise like in like 5 seconds. That's what we think, we know. But according to Zeno, we're wrong, and he can prove that we're wrong. So he argues that the tortoise is going to move at least a little bit. So suppose they hit a gong or something to start the race. So each of them starts to move, right? So if that's true, the tortoise is going to move, say, up to here, right? A little bit. Before Achilles gets to him, he's going to move a little bit, right? Move a little. All right. So the tortoise will get up to, say, over to here. Before Achilles can get up to that point where the tortoise has now got to, he's first got to get to where the tortoise was originally when the race started. Okay. So that's here. So Achilles has to get up to here. Okay, and by the time you get up to there, the tortoise has moved up to here, right? Whatever small amount that is, even if it's only like 6 inches or 2 inches, whatever, right? He's moved a little bit, right? So first Achilles has got to get to this point where the tortoise started. Then Achilles has got to get to this point here, right? But then the tortoise will have moved a little more, though less than he moved over here probably, right? Because he's much closer, right? Achilles is much closer to the tortoise, so tortoise moved less, but a little bit. Right? So instead of moving that much, he moves this. So now he's here. Now Achilles has got to get from here to there. So he does that, then the tortoise moves over to there. And then Achilles got to get to there, but then the tortoise has moved over to there, and so on and so on. So will Achilles ever catch up to the tortoise? No, it's impossible for him to overtake the tortoise. So that's a strange result. He'll get closer and closer to the tortoise, but he'll never actually reach him according to this argument. So our senses are just completely messed up.
Was he the same one that did the similar argument with the arrow? You could shoot the arrow.
Well, that's a third argument.
Okay.
That's actually the third argument.
Okay.
The arrow. Okay, so the arrow argument says, suppose an arrow is shot into the air. Well, so here's your arrow flying through the air. Then he says, suppose you consider the arrow at a single instant. Suppose you had a camera with like a super fast shutter speed, right? Like a godzillionth of a second shutter speed, right? It's monstrously fast shutter or whatever. It would capture it basically at an instant, say, though not technically, right? Because an instant is like 1 over infinity, right? So he says, imagine its speed at an instant. Like, how fast would it be going? If you took a picture of it while it was flying through the air with this really fast shutter speed, how would it show the arrow? As perfectly motionless, right? Yeah. So at a given instant, extending the analogy, the arrow would be literally motionless at any single instant, right? That seems true. Because at that single instant, there would be no time for it to move, right? And that seems to be borne out by taking a picture of the moving arrow with a really fast shutter speed. It'll just be frozen. Okay. He then says that since it's completely immobile at a given instant, and since an interval of time at which it allegedly moves is nothing more than the sum of these immobile instants, you can add as many of them together as you want. You won't get any speed by adding 0 to itself. An infinite number of times, it would still be 0. So the arrow is motionless. So that's the argument of the arrow. Then there's the argument of the dichotomy, which goes like this. It's kind of similar to the tortoise argument, but it's a little different. The dichotomy argument says basically that for something to move, for an object to move, that object must perform an infinite number of actions or tasks. But it's impossible for an object to perform an infinite number of actions or tasks in a finite interval of time. bouncing a basketball an infinite number of times, say in 1 minute, that's impossible. But he's saying that in order for something to move, an infinite number of tasks would have to be performed for it to move any distance, like an inch, or a yard, or a mile, or whatever, or a hundredth of an inch. In order for a thing to move any distance, an infinite number of actions or tasks would have to be performed by the object in question. It's impossible for that to happen, therefore nothing can move. So, obviously the main premise that has to be defended here is that for something to move, it must perform an infinite number of tasks. So here's the argument for that premise. So you have here an object, and we call it object O. In order for O to move, say some distance, say to here, in order for O to get from here to here, O first has to get to the midpoint between the destination and the starting point, which is here. That's the midpoint, M. In order for O to get to the destination, it's got to get to the midpoint first. Okay. But before I can get to that midpoint, it has to get to the midpoint between M and the starting point, which is here. So this is task 1 it's got to do, get to the midpoint. And task 2 is the getting to the midpoint between the midpoint and the starting point. Task 3 it's got to perform, of course, is to get to the midpoint between this midpoint and the starting point. Task 4 is to get to the midpoint between this midpoint and the starting point. So clearly, it's got to perform an infinite number of tasks to move at all any distance, and therefore motion is impossible to. So he's got the paradox first that the tortoise, that Achilles can never catch up to the tortoise, which he thinks he can prove there. It's kind of similar to the reasoning there, right? What's the common premise here? That first of all, there's an appeal to the idea of infinite divisibility. So Zeno assumes that space, at least, is infinitely divisible. That seems a pretty plausible assumption. In fact, it's still at least a working assumption of physics and physicists that space and time can both be infinitely divided. This is kind of implied. This is implied by the use of real numbers in science to do calculations about motion and time and distance. So they use mathematics and real numbers to calculate these. So it yields results in the equations of physics in which you have real number values for points of space. So basic assumption is that space can be viewed as a continuum, like the space-time continuum, which means that between any two spaces, between any 2 points of space, there's a point in between. That's called density. So it's said that both space and also time, in the sense that between any 2 points of time, like between 12 o'clock and 12:01, there'll be some time in between. That's called density. So space and time are thought to be dense, meaning that between any 2 points of space or instants of time, there'll be a point of space in between the 2 points and an instant of time in between the 2 instants. That's density, which entails infinite divisibility, because you can always divide the thing. Divide any space into 2 separate spaces, where there's a boundary between the 2. Density is entailed by what's called continuity. Continuity is an even stronger property than density. Continuity says that there's a one-to-one correspondence between every point of space or every instant of time and the real number line. So the rational fractions, the sequence of or series of rational fractions, right, like 1/2, 1/4, or 1/8, and so on, are dense, but not continuous, whereas the real number line is dense and continuous. Right? So continuity is like super density. Continuity, in effect, says that between any 2 points you have an infinite number. Points, an infinity of a certain sort. The infinity of real numbers, which, as we've noted earlier, is a greater infinity than that of natural numbers or fractions. So at any rate, Zeno assumes that there is that space and time are dense, infinitely divisible at least. Scientists back then didn't have a clear idea about the distinction between density and continuity. But at the very least, space and time can be divided forever, always getting smaller and smaller. So you see here, right? He gets to here, and to here, and to here. And these keep on getting smaller and smaller and smaller, but he can never quite catch up. He's going to be almost catching up. I guess there'll be a point at which he is, like, as far as you can tell, even with a turtle, he'll still be a little bit behind. The problem is, of course, we know that Achilles left the turtle in the dust, like right at the very beginning. That's the problem. Right? He just goes right by him. He's not doing this thing. First going to that half. But Zeno's right. He does have to first get to that half. And turtle. But I think the more general form of the argument is showing that there can't be any motion at all because the object has to make infinitely many movements before it can go any distance at all, which clearly it can never do. So Zeno sees paradoxical implications through this idea that that space is infinitely divisible, arguing that no motion, in that case, no motion is possible at all. So there are various attempts to reply to this. One would be to deny that space is infinitely divisible, and to say that there are, so to speak, smallest units of space which have a finite size, and possibly also a similar view about time. This is known as the quantum view. It says that space and time are quantized. That is, if there's a minuscule little minimum space that you can have. And beyond that, you can't divide that space into smaller spaces. But that minimum space is not a point. That is, it has, a thing could move in that minimum space. But you can't divide it into other points. You could strike one as paradoxical in itself, right? That you could have some tiny little area or whatever such that it can't be divided into two different areas, like the right half and the left half. Yet an object can move inside that little area. Some physicists today favor such a view, although, as I've said, sort of standard science still uses real numbers to describe space and time. It's not a settled issue, it's just a theory. The idea is usually put forward in the form that there's a minimum distance definable in terms of what's called Planck's constant. which is some inconceivably small number. I forget what it is, it's like 10 to the minus 30 something, whatever, times 1.1. Right, so it's expressed in some kind of form such as that, really tiny little area, distance. And here again, it's fueled by sort of verificationist ideas that that's the smallest measurable distance allowed in physics. Anything below that is, anything smaller than that is can't be dealt with because of the laws of nature. So if we can't verify anything smaller than that, that's the smallest space possible, or something like that. So if you have temporal atoms, then you would block this argument, right? Because then you couldn't keep on dividing forever. So that'd be one kind of response you could make. So we have here a question about the ultimate nature of space and a parallel question about time. Are they dense and continuous, or are there minimal spatial atoms and minimal temporal atoms, such that there's no time shorter than that minimal time, even though it's not an instant itself, and no distance shorter than that distance, even though it's not a zero distance. So that's an unsettled question in physics and philosophy and metaphysics as well. Well, we've reached our ending time here, so I'm going to stop and we'll continue with